Lesson: Explainability in Neural Networks. Explainability in neural networks has emerged as a pivotal focus within the realm of artificial intelligence, particularly as neural networks become more complex and their applications more widespread. The necessity for explainability is underscored by the demand for transparency, accountability, and trust in AI systems. As professionals in the field of AI implementation, understanding and applying explainability techniques is paramount. This lesson delves into the core principles of neural network explainability, offering actionable insights, practical tools, and frameworks that can be directly implemented to enhance the transparency of AI systems. Neural networks, particularly deep learning models, are often criticized for their black box nature. This opacity can hinder their adoption in critical sectors such as healthcare, finance, and law, where understanding the decision-making process is crucial. Explainability aims to demystify these models by providing insights into how inputs are transformed into outputs. A primary method to achieve this is through feature attribution, which assesses the contribution of each input feature to the final prediction. Techniques such as SHAP and LIME are widely used for this purpose. SHAP values, grounded in cooperative game theory, offer a unified measure of feature importance by considering all possible feature combinations. This method allows professionals to understand the influence of each feature comprehensively. LIME, on the other hand, approximates the local decision boundary of a model by perturbing the input data and observing changes in predictions. Both tools can be seamlessly integrated into existing workflows, offering interpretable outputs that enhance model transparency. Another critical approach to explainability in neural networks involves visualization techniques. Visualization can illuminate how data flows through a network and how different layers transform this data. Saliency maps, for instance, highlight regions in input data that significantly influence the model's prediction. These maps are particularly useful in image classification tasks, where they can identify which parts of an image are most relevant to a given classification. Furthermore, techniques like TSNE can project high-dimensional data into a two-dimensional space, revealing patterns and clusters within the data that may not be immediately apparent. By employing visualization tools, professionals can gain a deeper understanding of model behavior, facilitating the identification of potential biases or errors in the decision-making process. Beyond feature attribution and visualization, model simplification is another strategy to enhance explainability. Simplified models, such as decision trees or rule-based systems, can approximate complex neural networks while maintaining interpretability. Techniques like distillation allow for the transfer of knowledge from a complex model to a simpler, more interpretable one. This process involves training the simpler model to replicate the outputs of the more complex model, thereby retaining performance while gaining transparency. Model simplification is particularly beneficial in scenarios where decision transparency is critical, ensuring that stakeholders can understand and trust the AI system's outputs. Case studies further illustrate the practical applications and benefits of explainability in neural networks. In the healthcare sector, for example, a neural network model was developed to predict patient outcomes based on medical records. By employing SHAP values, the development team identified that the model heavily relied on a feature related to patient age, which was not clinically justified. This insight prompted a model revision, leading to more balanced feature usage and improved clinical relevance. Similarly, in the financial sector, a bank implemented LIME to interpret loan approval models. By understanding feature contributions, the bank was able to identify and mitigate biases in the model, ensuring fairer lending practices. Despite the advancements in explainability techniques, challenges remain. A significant obstacle is the trade-off between model complexity and interpretability. As neural networks grow in complexity to achieve higher performance, their interpretability often diminishes. Balancing these competing demands requires careful consideration and judicious application of explainability tools. Moreover, the effectiveness of explainability techniques can vary depending on the context and the specific neural network architecture. It is essential for professionals to tailor explainability strategies to their unique use cases, ensuring that the chosen methods align with the model's complexity and the domain's requirements. The ethical implications of explainability also warrant attention. As AI systems increasingly influence decisions with significant societal impact, ensuring transparency and accountability becomes a moral imperative. Explainability tools not only enhance technical understanding, but also support ethical AI development by enabling stakeholders to scrutinize and challenge AI decisions. This scrutiny is crucial for maintaining public trust and avoiding unintended harm. In conclusion, explainability in neural networks is a multifaceted challenge that demands a combination of feature attribution, visualization, model simplification, and ethical considerations. By leveraging practical tools such as shape, lime, and visualization techniques, professionals can enhance the transparency and trustworthiness of AI systems. Real-world examples demonstrate the tangible benefits of these techniques, highlighting their role in improving model transparency and mitigating biases. As AI continues to evolve, the principles and practices of explainability will remain vital for ensuring that AI systems are not only powerful, but also understandable and accountable.